The quantum physics, and the topic is the photoelectric effect, and this experiment was done by Albert Einstein in 1905 to prove that light is made up of particles. Light has a particle character, right? So already we discussed that he took a glass tube, right, and he took out the air. The glass tube was like a vacuum condition, right, and he put the two electrode. So the photons, they strike on the one electrode, right, and then photon, they transfer their energy to the electrons of the metal, and the electrons, they come out and they start moving to the other electrode, right. So when we put the negative potential of the other electrode at one stage, the electron, they stop, right. So the negative voltage at which they stop, that is known as the stopping potential. Okay, so if we see the first graph, in the first graph it's a photocurrent versus voltage graph. So photocurrent, it is in nanoampere, very small current we will get, which is in nanoampere, and voltage is taken in volt. Okay, so at stopping potential, all the electrons, they are stopped by the negative voltage of the other electrode, right. So at this point the photocurrent becomes zero, right. At Vs minus Vs, which is a stopping potential is a negative voltage. At that negative voltage, the photocurrent is zero. Okay, so now as we start increasing, or we can say as we start decreasing the value of negative voltage, means we start moving in this side towards zero. Okay, we start reducing the value of negative potential. So as we reduce, you see the photocurrent that built up, and when the voltage becomes zero, right, at that voltage we get a value of current, right, the photocurrent. So this is the value of photocurrent when the voltage is zero, right. So how it is possible when there is no voltage? Because automatically the electrons, they have kinetic energy. So with that kinetic energy, they will strike to the other electrode, and then they will create a current, right. They will make a loop, they will create a current, and that is a photocurrent. Now finally, when we start increasing the voltage, means now we are in the positive region of the voltage. Positive voltage we are giving. So when we give the positive voltage, okay, so current, again current that built up, right, because more and more electrons, they are attracted by the positive electrode. So the current, the photocurrent, that increases, and at one particular value of positive voltage, the photocurrent that becomes maximum photocurrent, right. And after this positive voltage, if further we keep on increasing the voltage, the current does not increase. So this is a saturated region, right. Means the maximum photocurrent now that will flow, right, maximum value. Now beyond that, if further we increase the positive voltage, right, the current will not cross that maximum value. Why? Because the maximum electrons, the maximum limit of the metal, right, that is achieved. So at that maximum limit, it can give the maximum number of electrons. So corresponding to the maximum number of electrons, we can get the maximum value of current. So if further we increase the voltage, there is no use of that. So okay, so we will stop here at this voltage. Okay, so the graph from this point to this point is important. So the conclusion is that if the next stopping potential is there, right, the stopping potential that will stop the photoelectrons. When the photoelectrons are stopped, then the photocurrent becomes zero. And if we reduce the stopping potential, we move towards zero, then the current start increasing. And finally, in the positive range of the voltage, the current also increases, and finally it attains a maximum value. Okay, so this is maximum photocurrent, right. Now if we go to the second graph, in the second graph already it's a photocurrent versus voltage graph, but I took two sources. One is the bulb, right, which produces a white light. Bulb is a source of white light. Candle is also a source of white light. So if we compare the bulb with the candle, so which type of graph we are getting the photoelectric effect? You see, the both graph, they originate from the same stopping potential, right? Means the value of stopping potential to stop the to stop the photoelectrons coming from a bulb, right? The light from the bulb, the strike the metal, emit the photoelectrons. So you see, the common value of stopping potential is there for both bulb and candle. Why? Because if red light is coming from bulb, right, having certain frequency. The same red light will come from the candle, right, because both are sending the white light, right, both are sending the white light. So it means if we see the red color, then definitely for the red color, red photon, they will be stopped. The red photon from the bulb and the red photon from the candle, they are same. The violet photon from the bulb and violet photon from the candle, they are also same. So if they are same, right, if they are same, they have the same frequency, because they have the same wavelength. They have the same wavelength, they have the same frequency, they have the same energy also. If they have the same energy, to stop that energy, it means the fixed stopping potential will be there. Okay? If they have the same, because frequency of red in case of bulb, frequency of red in case of candle, same. Okay? When frequency is same, then energy is same. If energy is same, then definitely the stopping potential will also be same. Right? But the difference is that you see this y-axis, you see the photocurrent. In the bulb, the intensity of the bulb is more than the intensity of the candle. So it means more intensity means large number of photons. So bulb send more photon as compared to candle. More photon will strike the metal, they will eject more electron from the metal. Okay, Michaela? Yeah. More photons strikes the metal surface, they eject more electron. More electron mean more photocurrent. So photocurrent in case of bulb, that will be greater than photocurrent in case of candle, right? So now what intensity do? Intensity that just send more photon, and corresponding to that more electrons will be emitted, right? Now if we go to graph 3 is very important for us, right? So the graph 3 is a graph between kinetic energy of the emitted electrons. It's not kinetic energy of the photons. It's a kinetic energy of emitted electrons or kinetic energy of the photoelectrons. Okay, versus frequency of incident photons. Okay, kinetic energy of emitted electrons versus frequency of incident photons, right? So kinetic energy, that is taken in joule, and frequency is taken in hertz. Okay, so again the kinetic energy of the emitted electrons, which are photoelectrons, and the frequency of the incident photons. Now what happens? You see, from this graph you focus on this point having the frequency Fc. So if we start from zero frequency from here, so zero frequency to critical frequency Fc, you will see, right, you will see there is no kinetic energy. Kinetic energy of the photoelectron, that is zero, right? Kinetic energy is zero. But now if we increase the frequency, means we increase the frequency of incident photons, right? So now as the frequency increases, the kinetic energy of the emitted photoelectrons, the kinetic energy of the electrons emitted from the metal surface, that will also increase. Okay, so now because this is a straight line, experimentally we are getting a straight line, so we can conclude that the kinetic energy of the emitted photoelectrons, that depends directly on the frequency of incident photons. Directly, because this is a straight line. So direct relation. But there is a critical frequency. There is a threshold frequency. Below that frequency, no emission, no kinetic energy. Right? Below that critical frequency, below that threshold frequency, ejection or emission of electron from the metal is not possible. But if we cross the critical frequency, if we cross the threshold frequency, then we will get a direct relation, right? Any change in frequency, right, that will be a direct change due to change in energy. Or you can say any change in energy of the incident photons, that will give a proportional change in the frequency, right? So the graph 3 is very important, but keep in mind the kinetic energy is of the ejected electrons versus frequency of incident photons. Okay, Now finally, miss, we go to graph 4, and in graph 4 again you see it's a relation between photocurrent and voltage. Now again we do experiment for different colors. So now I choose two color. One is the green, other is the red. So the graph 4 that tells us that the stopping potential depends on frequency of incident photons. How? How? So you see we have two different stopping potential. One for green, other for red. And you can see the stopping potential for green is more than the red, right? Why? Because if you see the frequency of green is Fg, the frequency of red is Fr, and if you compare, the frequency of green is greater than frequency of red. So when frequency of green is greater than frequency of red, definitely the energy of green that will be more than energy of red. Okay, so now we can say energy of green photons falling on the metal surface, that is greater than energy of red photons, right? Green photons, they have more energy, they have more kinetic energy, right? So when the green photons, they have more